until last lecture we discussed about effective mass, and I also said that effective mass can be negative, can be positive, can be very small, can be very large, and so on and so forth. So, one of the things that I did not mention at that time, but I should mention it now, is that so far the nearly free electron model that I have discussed has ensured the following things. Nearly free electron model has explained why some materials are metals and why some are insulators or semiconductors. So, this was possible because of the idea of the band gap. Whenever you have a band gap and you have a filled band, then you will not have any conductivity, and if the band is partly occupied or partly filled, then you will have conductivity, and the difference between insulators and semiconductors is purely quantitative. Insulators have very large band gaps, but semiconductors will have smaller band gaps. So, you can thermally excite carriers across from the lower band to the upper band, from the lower fully occupied band to the empty upper band. This is one thing. And secondly, one of the other things that I mentioned when I started talking about the failures of the free electron model was that some metals like aluminum have positive Hall coefficients. This implies charge carriers have a positive sign. Well, we discovered that electrons at the top of the conduction band have negative effective mass. What it means is that we can treat electrons at the top of the band as holes, which is positively charged, and mass positive. This implies that you have the negative effective mass is treated as positive with charge changing sign. So, and we know that aluminum is some kind of an overlap metal, and so you will have the particles the partly this thing occupied band at the top, and so we will have this can explain how materials can have, how metals can have positive charge carriers. Okay, or holes. So, this explains the this thing strange Hall effect result that one obtained. One more thing I want to say before I go on to other things in under the effective mass banner, and that is to say that if we look at the energy dispersion, of free electrons is E is equal to h cross squared k squared by 2m. But in metals, E is a complicated function of k, which you have to work out for every material. That is the energy band theory. So, that means E of k is not a simple function. So, if you want to treat electrons in metals as free electrons, then we have to think of changing the description, the definition of mass. If we wish to use free electron expression for energy in metals, we need to replace the electron mass by an effective mass. So, what we are saying is that E of k, actually I did not use a script, E of k you can still say is h cross squared k squared divided by 2m, except that m is not the bare m but m star. M star is the effective mass, and m star has a definition that already has been given, that is m star is actually is a tensor and given by 1 upon m star I j is equal to 1 upon h cross squared del squared E by del k I del k j, where I j etc. take x, y, z values. So, we see that the effective mass is no longer a scalar in general, but it is a tensor. But you can also measure effective mass by various experiments. For example, if we can measure effective mass can be measured from plasma resonance. It can be measured from what we call cyclotron resonance, or through optical spectroscopy. But the thing is that the effective mass that is measured by different methods gives you different values, simply because the effective masses are actually measured are averages. The measured effective mass are averages, and the way averaging is done depends upon the experiment. So, each experiment does the averaging differently, and so you will have different effective masses. Well, now let me go on to some devices which depend crucially on the variation of the effective mass. Okay. So, like I already said that if a band is narrow, effective mass is small. If a band is broad, effective mass is large. There are materials like gallium arsenide, gallium nitride, cadmium telluride, indium phosphide, cadmium sulfide, indium antimonide, indium arsenide, and zinc selenide, some of the well known semiconductor materials. They have a very interesting band structure. They have a band structure with a narrow valley separated from a broad valley. For example, in the case of indium gallium arsenide, we have the following band structure. So the band structure energy versus K, if I plot, it is something like this. This is the narrow valley. Here the effective mass is about 0.07, 0.72 or 0.78, something like that, and this is the broad valley. Effective mass in this broad valley is about 1.02. So the barrier to the broad valley from the narrow valley is about 0.36 electron volts. Okay, so you have to climb a barrier of about 0.36 electron volts from the narrow valley in order to go to the broad valley. I think now let me see what is the consequence of this one. So supposing I start with an electron somewhere here, okay, and I apply an electric field. So applying an electric field will give me the following. Will yield a current, and the electron starts moving up the band structure. Moving up the EK curve. So what we mean by that is that as I start applying the electric field, it starts moving up like this. So beyond a certain electric field, the electrons begin to populate the broad valley. So what happens when the electrons start occupying the broad valley? The effective mass of the electron goes up, so if the effective mass of the electron goes up, then the resistivity increases. So when the electrical resistivity increases, the following thing happens. So supposing I started with my sample somewhere here, and I started applying an electric field, the electron starts moving, okay, and this is the electric field, let us say. Then as I go to higher and higher electric field, the electrons get completely the electron density builds up because the electrons are not going to be moving as fast because of the large effective mass, and this density build up in the electrons, what it does is it reduces the electric field that is being applied, and so less and less of these electrons are getting occupied in the lower valley, and this happens until this comes and gets discharged at the end, and again you start the cycle. So basically what we have is the current begins to oscillate as there is a build up and then a discharge and a discharge, and this happens repeatedly. So when this happens repeatedly, then there is an oscillation in the current, so the current oscillates, and oscillation of the current gives rise to microwave generation. So the microwave that is generated is usually for the gallium arsenide case. The microwave frequency can be anywhere between 10 gigahertz to 1 terahertz. So you can actually generate the microwaves using gun effect oscillators. This was actually first observed by Gunn at IBM, and he expected it based on the picture of the this energy bands, and based on the energy band calculations that were available at that time. I think it was available, I am not sure, but there was some preliminary energy bands, and either there was some preliminary energy bands, or he explained based on the narrow valley and the broad valley concept what he had observed. And this Gunn effect oscillators are used quite extensively in various applications. Gunn effect oscillators are used, say for example, in speed detecting radars, various kinds of sensors, and is good whenever you want low power microwave generation. There are a large number of applications of Gunn effect, and this is one of the direct application of this effective mass changing within the band. Yeah, and then so this one of the applications. We also find something else, that is in any case, there have been applications based on Gunn effect oscillators. Now we go over to a different aspect of this motion of electrons in an applied electric field, and we will see how, for example, I said that we have insulators corresponding to a filled band. Now the question is that how does an electron move when you apply an electric field in a metal and in an insulator? Both of them is very similar, and when will the insulator break down? Because it is known, for example, that when you apply a very strong electric field, then an insulator breaks down. So this breakdown of the insulator is called Zener breakdown. under very high electric fields. So, how does one understand that? So, the way to understand that is following, that is, supposing I have got a electron in an energy band, then let me look at it in the K space in a repeated zone representation. So, if I look at it in the repeated zone representation, if I have energy here in the repeated zone representation, the energy is going as in the form of a wave. So, this is K. Now, I apply an electric field, then what happens is the electron that is here, that is, if I draw just one single band, I can show you, and so the electron that is here starts moving up and reaches the point A, and when I increase the electric field, then what happens is that this electron gets scattered back, because there is a band gap and it cannot cross the band gap, and since it cannot cross the band gap, it gets reflected, because and another way of actually looking at it is that is the Bragg reflection, or that the effective mass here has an opposite sign, because of which the electron starts moving backwards. So, it comes here and then again starts its journey back. So, basically it is cycling between minus pi by a and pi by a. The electron is actually going around. When you apply an electric, as you keep ramping up the electric field, this is what happens, and that is what is shown here in the repeated zone scheme for a single band. Now, it is important to see what happens in the real space. What is happening, there is also one can also look at it slightly differently, in the sense that if I have the bands like this is an upper band, okay, and I have the lower band. When I apply an electric field, these bands will bend. So, an electron somewhere here would cross over to the upper band, provided the distance d it travels, it gains enough energy, that is E times d, which is the energy gain when an electron travels a distance d. If this energy gain EED is greater than, let us say, the band gap, then electron will jump to the upper band. So, another way of looking at it is, you have the upper band here and you have a lower band. So, this is E, this is K, and this is the upper band, let us say A is the position and A prime here. So, if from A to A prime it should jump, that is, if it has to jump from this band that I am showing here to this band, then it should travel a distance d under the influence of a field, such that the energy it picks up is greater than the band gap. So, if that happens, it can actually jump and you will have the breakdown of the insulator. Another way of actually looking at it is as a tunneling problem. So, in the tunneling problem, what one is looking at is the following. So, let us assume that the band gap is Eg, then the probability of tunneling can be computed can be computed using a simple WKB approximation. From tunneling. So, what one will get in that case is that the probability will be of the order of this one. It will be of the order of e to the minus pi squared by 4 times E gap squared divided by E0 EEA. So, here E gap is the band gap, E0 is the energy at the zone boundary. And A is the lattice constant. So, if I pick up an energy which is E times A, which is roughly E gap, then my probability will be e to the minus pi squared by 4 into E gap upon E0, and if the gap is small, then the probability is high. If the gap is small, the probability is high. And the probability is also high if energy at the zone edge is also high. So, we can have a Zeno breakdown if an insulator, if the energy gap in the insulator is small. So, these are some of the things that you can learn from looking at the dynamics of nearly free electrons in materials, and what I have shown is that you can have interesting phenomena like the gun effect coming out because of the differences in effective mass in different regions of the energy band, and also if the band gap is small, even an insulator can start conducting electricity, or you can have a breakdown of the insulator by applying very high electric fields. So, next what I am going to do is to look at how to compute the effective masses in the case of some using a band structure theory. Okay, how to compute effective mass from energy band theory. And this has been done using perturbation theory, and I will talk about it in the next lecture. And with the next lecture, what I will be doing is I will be completing the basics of energy band theory, that is the terminologies and the various concepts that come about in energy band theory. And after the next lecture, probably in the next lecture, I will give a brief introduction to what I would be covering for how to go about doing energy band calculations. And after we discuss some of these methods of doing energy band calculations, we will go over to other phenomena which are beyond energy band theories. So, I think I will stop this lecture at this point, and we can start on computation of the effective mass from energy band theory in the next lecture. Thank you.